Okay, so today we are gonna discuss what's the element, the 3D element, uh which is subjecting to the loading. Okay, any loading can be action loading or torsion or bending and so on. So if we just look at a small element, infinitesimal small element, and this 3D element should be subjected to the normal stress on each surface and the shear stress on each surface, right? Therefore, we can uh, make this infinitesimal element as a point, okay, as a point. And the coordination can be arbitrary, and we choose the coordinates which result in the zero shear stress will produce the principal stress. Okay. So if we just ignore the any stresses in z direction, we can regard this point element as the plane stress. Okay. So if we just ignore the any stresses in z direction, we can regard this element as the plane stress, right? Plane stress. Okay, so okay, so suppose we have the element like this. There's a uh there's a rod, right? There's a rod, a fixed rod, okay, solid rod, which is subjecting to a torque and a point load, right, at this free end. Okay, so if we just pick up a infinitesimal element or a point at B and A. So what kind of the stress applied to these 2 points should be? Okay, so in the point A, at this point, right? Point A, right here, point 8. So what those stress applied to it? So the torque T produce the shear stress, right? So if you still remember that for the torsion, the maximum shear occur at the surface of a solid rod, right? So at point A, it should have the shear stress, right? Due to the torsion, right? And what's the value of the torsion? Which is TC, T times the distance from the neutral axis to the surface, right? Or say the radius of this solid rod divided by the polar moment, right? The shear stress. And what else? What else? So at the point 8, which has the transverse shear due to the bending from the central load P, right? So they must have the transverse shear stress. Okay. So if we plot the plane stress, because we just look into the point A, we regard as a point. For sure, it will be the plane stress, right? Situation. Okay, so if we just focus on the point 8, there are two types of the shear stress applied to it, right? One is the shear stress from the torsion, right? And the second shear, which is from the pure bending, right? Pure bending. So if we just look into the plane stress of the point A, it should be subjected to two shear stress. Okay, two shear stress. Okay, right? And we can regard this point A is located at the center, okay, the center of the solid rod. center of the solid rod. So the second case is the point B. The element B is on the top of this solid rod, right? So the same, the point B is still located at the surface of the solid rod. Therefore, it's still subjected to the shear from torsion, right? From torsion, right? From torsion. Okay, so what else, right? The same, the bending still, right? So on the top surface, it should be a tension, right? Tension or the normal stress, the maximum normal stress on the top surface, which is under tension, right? Therefore, there's the normal stress from bending, right? From bending. Okay. So if we look into any point, either A or B, and we rotate the specific angle, we can reach the other specific stress value of the sigma x and the tau x, sigma x and tau xy in the different coordinates. So we can put this notation prom on it. Okay, that's mean the second coordinate. Okay, the second coordinate. When we say we rotate the specific angle, we will reach what? The principal stresses, right? From the previous slide, we already mentioned that. When you rotate the angle, this element A or B will reach the principal stresses. Okay. Okay, so if we look into infinitesimal element with the normal stress and the shear stress applied to it. Okay, so if we just cut through any angle, I mean, we just slice this infinitesimal element with a specific angle. Okay, this way or this way or this way, doesn't matter. Okay, so and then we can analyze the stress distributed on this element with the different coordination system. Okay, so suppose we already slice this small element with a specific angle, right? And originally we have the Cartesian coordinate, right? And then we can transfer this Cartesian coordinate to x prime and y prime. Originally it's x and y, right? So we can transfer from xy to x prime and y prime, which is based on the surface with the area delta A. Okay. And then we can use the equilibrium equation to analyze this free body diagram. Okay. So, wow, I think you guys must feel really familiar with this equilibrium equation, right? Sigma fx equals to 0 and sigma fy equals to 0. However, in this case, we have to base on the coordinates x prime, y prime. Okay. Okay, so the force applied to this element, the surface of this element, sigma x prime applied to the surface perpendicular to this surface delta A, right? Therefore, we just use the sigma x prime multiply by the surface, we get the force along the x prime direction, right? So we get the Fx, right, in x prime direction, right? However, there are other forces or stress, right, applied to the different surfaces, right? So for example, this sigma x, applied to this surface, right? How to figure out this surface area? It is equals to the delta A times cosine theta, right? So you know the surface area of delta A, on this surface is delta A, right? So delta A times cosine theta equals to the area of this surface, right? And the sigma x times the delta A cosine theta equals to the force, right? The force here in this direction, right? So, and then if we use this triangle here, right here, and this is the force, right? The force, and this is the theta, right? And the force, right, times cosine theta, right? We'll get the what? The component of this stress and force along to the x prime direction, right? Should be this direction, right? That's why here's the minus, right? It's the minus, right? And in positive x prime direction is positive sign, right? So the same thing, we can analyze the different, stresses, right, along to the x prime and y prime coordinates, right? Okay, so I'm gonna skip those mathematic process. Okay, you can work on this a little bit. Okay, I just want to show you how to analyze the stress on the delta A and along this x prime and y prime coordinates. Okay. Okay. Okay, and then we can figure out the sigma x prime, right, in terms of the sigma x, sigma y, and tau x y, okay, and the tau x prime y prime, right, corresponding to sigma x, sigma y, and tau x y, right, in terms of trigonometric equations, right? So we can now as well we can use these trigonometric equations, right, to figure out to transform the sigma x prime and tau x prime y prime, right? So we can plug here to here, right? Right, and here we can plug here, here, right? So we can rearrange the sigma x prime and tau x prime y prime. Okay, so we can convert the sigma x prime in the form of, in terms of the sigma x and sigma y and tau xy. Okay, so we can just rearrange this again. We can rearrange this again, right? So this term equals to cosine theta square, right? And this term equals sine theta square, right? Okay, so we can get this relations here. Okay, and then we can convert it to tau x prime y prime, right? In the term of the sigma x, sigma y, tau xy, and the 2 theta. Okay, so we just plug this 2 theta here, right? So we can get this equation, right? So it's just some mathematic works, okay? It's not difficult. Okay, so we're gonna figure out what the Mohr circle is. Use these two equations. Okay, we're gonna figure out what a Mohr circle is. So what is a circle? What's the function of the circle? Right? It should be the x squared plus y squared equals to r squared, right? R is the radius of a circle, right? Right. So if we plug any point on a circle, right? For example, right here, okay, right here, right? So it's right. So there's a theta here, right? It's r, right? Therefore, we know the x equals to what? R cosine theta, right? right? It's correct. And what is the y? Equals to r sine theta, right? And then x squared plus y squared equals to r squared because the sine squared plus cosine squared equals to 1. Equals to 1. Okay, so based on those parameters, and we can use the very, I know, very, it's elementary school math, right? To figure out the Mohr circle, to figure out the Mohr circle. Okay, so where's the Mohr circle? What the Mohr circle is? What the Mohr circle is? So let's go back to, sorry. Okay, let's go back to previous one. So from this sigma x prime, okay, sigma x prime, right? So we can remove the part, the first term on your left hand side, right? And square it, right? So move this from to your left hand side and square. So you can use the very fundamental mathematical relations right here, right? To get this whole terms on your right hand side, on the right hand side, right? And then this tau x prime y prime square, the same process, right? So we just squared it, right? So we get the right term like this. And then we can plug this sigma, these two equations, right? 1 and 2, okay? So this is 1 plus 2, okay? 1 plus the second equation, okay? And these two terms can be eliminated, right? And only this term plus this term, right? Is that clear? And then the cosine square plus sine square equals to 1, right? Right here, 1. The same thing, the cosine square plus sine square plus cosine square equals to 1 here, right? Is that clear? So we can get this equation. Well, we can see it's quite similar to a circle, right? X squared plus y squared equals to r squared, right? And the A represent the shift of the center, or say center shift, right? Okay, the center shift. Okay, and then we can say the radius of the Mohr circle. We define this as a Mohr circle. Okay, so what is this? Its radius is? It's this term, right? It's this term. It's the radius of the Mohr circle, right? And where's the center is? Where's the center is, right? Sigma x plus sigma y divided by 2 represents the center of Mohr circle, of the Mohr circle. Okay. Okay, so I'm gonna show you one examples here. Suppose here is an infinitesimal element in the plane stress, okay? And the sigma x equals to minus 10 megapar, which means compression, and sigma y equals to 50 megapar. It's a tension, and the shear stress tau xy equals to 40 megapar. Okay, so based on this, the known stress applied to this infinitesimal element, and we can get the radius of the Mohr circle, right? From the previous slide I show you, right? Sigma x minus sigma y divided by 2 plus tau xy squared. So radius equals to 50 megapar. Okay. Also, you can get its center, right? It's 20 megapart. Sigma x plus sigma y divided by 2, okay, equals to 20. Therefore, we have the center of the radius, and then we can plot the circle, right? We can plot circle. So here's the center. If the x-axis represent the sigma, okay, no more stress, and the y-axis represents the shear stress, the shear stress. Okay, so the center is 20, right here, and the radius is 50 megapart. Okay, and we can decide the points, the stress condition on this Mohr circle. Okay, so what that is? For example, we have the sigma x equals to minus 10, right? So I have to find where's the minus 10 is right here, right? Is a minus 10, right? For sigma x. And sigma y is positive 50, right here, right here. Right? And its tau xy is 40 megapart. What is the tau xy? The shear, right? So the positive 40 right here. Okay, therefore get the stress condition in y, okay, right here, right? Because the shear is 40, the 40 megapart, right? And this 40 is rotated in this direction, and we define it as the positive. Okay, the conventional sign is positive, and if this rotation direction in this direction, we define as a minus. Okay, minus. So we can figure out the stress condition at the y point and the x point, right? So we just connect these 2 points. We get the condition stress on this Mohr circle, x and y, x and y. Okay. Hey, what else? So from this circle, we can figure out where is its maximum shear stress is, right? So where's the value of the maximum shear stress? If suppose we have the stress condition at y and x, right? So this point, when this point is counterclockwise, right? Counterclockwise to the top point of this Mohr circle, where is the maximum shear stress? Okay, the same thing. This point we are rotated to right here. Okay, and if the point y rotated a specific angle clockwise, you will reach the principal stress. Right, the same thing. The point x, it's rotated coincide with the x-axis, we'll find its principal stresses. So we define this angle is 2 theta s and 2 theta p, 2 theta p. Okay, so from this triangle, from this triangle, this one, okay, this one, okay, this one, we can figure out what's the value of the theta p is. Therefore, the tangent to theta p equals to 10 over minus 30. So we get the angle as minus 26.6. Okay. Okay. So the tangent to theta p equals to 2 times the tau xy divided by sigma x minus sigma y. Okay, from this triangle. Okay, this triangle. Is that clear? So the same approach, we can figure out what is the 2 theta is. So the tangent 2 theta, right, from this triangle here, sorry, right? We can figure out from this trigonometric relation, right? So we can figure out what is tangent 2 theta is. And in this case, the theta s equals to 18.4 degree. Right? So from the Mohr circle, we can figure out what is the maximum shear stress is and what is the maximum normal stress is, representing the principal stress when rotating a specific angle, theta p or theta s. Right? So when this small element, this small element rotated 26.6 degree clockwise, what we get, right? We will this line xy, x and y, right? Will coincide with the principal stress, 70 megapart and minus 30 megapart. So we can plot the stress condition when the xy rotated angle with 26.6, right? So it will like this in this case. When it rotated 26.6, we get the normal stress of 70 megapart and the compression 30 megapart. Okay, and these two are principal stress. Okay, these two are principal stresses. Okay. On the other hand, if we rotated this small element counterclockwise, that means we rotated this x and y, right? Counterclockwise. What we get the maximum shear stress, right? Maximum shear stress. So the value of the maximum shear stress is, right, 50 megapart. All right. However, at this point, we will get the normal stress 20 megapart. 20 megapart. It's positive, right? It's on the right side of the origin, right here, right? So it's positive. So in this stress condition, when this element rotated 18.4, we'll get its maximum shear stress with the average normal stress. Okay, this is average normal stress. Okay, so I'm gonna make a connection between what you have learned for your material science course. So do you guys still remember where is the plan that's the sleep? What's the plan is most possible to uh, occur the sleep process? No, no, I'm saying. So suppose we have the uh, uh, a spaceman for tensile stress, right? Like this, the duck function, and we apply the force. So which plane, which angle is, which plane that is the most possible to trigger the sleep process? What the angle is? 45, right? 45. Suppose we have the FCC structure, the metal with the FCC structure, which plane, which Miller indices are presenting the closed pack plane? It's 111, right? So you will know the sleep process occur in the closed pack plane and direction. Okay, and angle is 45 degree. Okay, and angle is 45 degree. Okay, I just want to make some connection with the design and the material science. Okay. Okay, so I just want to say we can convert the coordinates from the Cartesian, right, to any plane, x prime, y prime. Okay, x prime and y prime. Okay. Okay, and so if we just ignore the component in z direction, and we can regard it as the plane stress. Okay, the most cases are plane stress. Okay, for example, I have the solid rod, and when it is subjected to a torsion, the maximum shear, where's the maximum shear stress? On the surface, right? On the surface. Therefore, we can regard the surface element is the plane stress, right? The plane stress. Okay, so I think you can refer to some definition of the footnotes. Okay, the footnotes. Okay, I think it's not quite difficult. And just summarize what I already taught us. So the cutting plane stress element at arbitrary angle and the balance stress give a plane stress transformation equation, right? So we can transfer from the sigma to sigma x, sigma y, and tau xy. So previously I just used the sigma prime, right? And tau prime, like this. Okay, the same thing. Okay. Okay, so and then we can use the transformation equation to figure out this theta p. P means the principal stress. That means when the Mohr circle, uh, when the point on the Mohr circle rotated, the theta p will reach the principal stresses. That's why we say the value of the 2 theta p is the principal direction. Okay, it's the principal direction. There are two values because we can rotate it clockwise and counterclockwise. Okay, so the stresses in the principal direction are principal stresses. And the principal stresses surfaces has no, without any shear stress. Okay, without any shear stress. So we can combine those equations to find the expression for the non-zero principal stresses. Okay, so sigma 1, sigma 2, that's mean the principal stresses. Two principal stresses, right? Two principal stresses. So you can notice that this is the center and this is the radius, right? The center of the radius. Okay, so notice that there is a third principal stress equal to 0 for plane stress. So we ignore the stress in z direction, okay, in z direction. Okay, so performing the familiar procedure with the shear stress, right? So the maximum shear, I already mentioned that can be found on the surface that are plus minus 45 degree, okay, from the principal direction. So the two extreme value shear stresses are, right? So we rotate it clockwise or counterclockwise, can reach the maximum shear stress, right? So the tau y and tau y2 represents the maximum shear stress, maximum shear stress. Okay, so suppose we consider the three principal stresses. That's mean the if, okay, and if one is 0, that's for the plane stress, right? If it's non-zero, so we have to take the three principal stresses into account, right? So if the tau 1, 2, tau 2, 3, and tau 1, 3, I will explain what it is. Okay, and the maximum shear stress is always the greatest of the three, right? And the previous equation, let's go back to uh, this equation, okay? This equation will not give the maximum shear stress in cases where there are two non-zero principal stresses that are both positive or negative. Okay, so the maximum shear stress is related to the principal stresses, whether it's both positive or both negative. Okay, So what's that mean? Okay, I will show you why. So remember that if the principal stresses are older, so that sigma 1 greater than sigma 2 and greater than sigma 3, we'll say the tau max equals to tau 1 3, this case. Okay, this case. Okay, so we'll go back to Moore's circle. We'll go back to Moore's circle. A graphic method for visualizing the stress states at point represents the relation between XY stresses and the principal stresses. Okay, and the parametric relation between the sigma is the normal stress and shear stress with the two theta, either is to a theta P or a theta S. Okay, the relation is the circle, Moore's circle, right? The center, right? The center, okay, the center and the radius, okay, the center and the radius. Okay, so let's look into the real case. That means the 3D, three-dimensional stresses. Okay, so for the plane stress, elements simply have one surface with zero, right? So in real case, if we plot this in 3D, what it should be. Okay, suppose we have the element, the same, the infinitesimal element. No, this element could be subjected to normal stress, compression, torsion, bending anyway, and we can just analyze in the small 3D element with the normal stress, and normal stress, and the shear stress, and shear stress. Okay, in 3D case, the thing we can cut in any, any we can slice this small element in any angle, Okay, and use the Moore circle to figure out its the principal stress and the shear stress and the shear stress. Okay, so we can plot the Moore circle, right, of this 3D case, right? So it rotated a specific angle will reach its principal stress, right? In this case, it's sigma 1, sigma 2, and sigma 3. And we just force this relation that has to be sigma 1 is greater than sigma 2 and greater than sigma 3. Okay, we have to follow this order. Okay, therefore there are three more circles, right? We can figure out three center. One is here, two, three centers, right? So there are three more circles. And where's the maximum shear stress? Where's the maximum shear stress? Tau 1, 3, right? This one. So that's why the previous slides mentioned that here, right? So if the principal stresses are older, in order of the sigma 1 greater than sigma 2 greater than sigma 3, so and then the tau max equals to sigma 1, the shear max, that's mean the maximum shear stress equals to the tau 1 3, right? So that's in this case. Okay, there's the maximum stresses is right here and here. So this is the maximum shear stress. Okay, and tau 1 2 equals to sigma 1 minus sigma 2 divided by 2 right here. And tau 2 3 right here equals to sigma 2 minus sigma 3 divided by 2. Okay. Okay, so that's why I mentioned we have to follow this order of the principal stresses, and we get the sigma, the shear max equals to tau 1 3. Okay. Okay, so I just show you the other figure. Maybe you can realize what the 3D, the shear stress in 3D is. Okay, so suppose this is a 3D element. So what its analysis should be? So is there any z direction no, stresses? No, right? In z direction, there are no any stresses applied to the surface, right? However, it's still in 3D element. So we got only the P means the principal stresses, okay? The sigma 1, sigma 2, and the sigma P3 or sigma 3 equals to 0, right? Because there's no any stresses applied to this plane, right? Right? So we can plot 3 more circle, right? Right, 3 more circle. And here is the maximum shear stress. Maximum shear stress, absolute maximum shear stress. Okay, right? And at this point, it's just in plane. The maximum shear stress in plane. In which plane? In which plane? In this plane, right? And this point is it's also the maximum shear stress in plane. In which plane? In this plane. Okay. Okay, so just briefly summarize what I already told is the maximum in-plane and maximum absolute shear stress. You use the Mohr circle, right, for the 3D element case, right? For example, in this case, there's no stresses, right, perpendicular to or applied to this plane, right? That's mean the sigma 3, P3 equals to 0. So we have to sigma 1, sigma 2, and sigma 3. And we can plot 3 more circle and to figure out what is the absolute maximum stress, shear stress. Okay, so for this case, that's the sigma 1, P1 and sigma P2 are both positive, right? Positive. That's what I mentioned previously. They're both positive. And the maximum shear stress, the absolute maximum shear stress equals to sigma P1 minus sigma P3, right? And the P3 equals to 0, right? Okay. And if this sigma P1 and sigma P2 has the opposite sign, that means sigma 1 times sigma 2 is minus, right? It's the minus. In this case, the absolute maximum shear stress will equals to the in-plane maximum shear stress and equals to sigma P1 minus sigma P2 divided by 2. Right, so sigma P1 right here and sigma P2 right here. Okay. So and usually we always define the order sigma 1 greater than sigma 2 and greater than sigma 3. Okay. Okay, so Hooke's law. What's the Hooke's law? This equation, right? Present the Hooke's law, right? Only in, right? So if we apply the stress strain curve, right? So this equation represents in this in this elastic region, right? It's a linear relation. Therefore, the E is the slope, right? Just recap some mechanics course. The E is right here. So E is the Young's modulus or the modulus of elasticity. Okay, tension in the direction produce negative strength in the perpendicular direction. Okay, so that's mean when we apply a tension, right? So one direction will be elongated and the others will shrink it, right? We are shrinking. Okay, we are shrinking. So if say in the x direction, right? So if this tension x direction in x direction, right? So the strength, the actual stresses in x direction, we can figure out its strength in x direction, right? Equals to the sigma x divided by the Young's modulus. And how about in y and z direction? It should be shrinking, right? Its dimension should be reduced, right? Therefore, say the stress in y and z direction equals to sigma x times parameters. It's a materials property called Poisson ratio. Okay, called Poisson ratio. Okay, Poisson ratio. Okay, so we got this relation of the elastic strength. For a stress element undergoing this sigma x, sigma y, and sigma z simultaneously, and we can figure out its strength in x, y, and z direction. Okay, it's a function of Poisson ratio. Okay, it's a function of Poisson ratio. Okay. Okay, also for the shear, that means suppose we have the solid rod undergoing a torque, right? Undergoing a torque. So this G represent what? The shear modulus of elasticity or the modulus of rigidity, or we say the shear rigidity, okay, the same thing. And the gamma represent the shear strength, okay, the shear strength. And for the linear isotropic homogeneous material, this relation between the Young's modulus, the modulus of a rigidity and the Poisson ratio, they match, okay? So remember, this equation is only can be only used for when this materials in linear, isotropic, and homogeneous. Okay, so we can think of what kind of materials cannot satisfy with this equation, like composite, right? So maybe with the fiber direction, when we mix some fiber with some rinsing or epoxy, right? Maybe the fiber direction dominate the strength of this composite. In this case, this relation is not available. It's not available because it's not isotropic. Okay, it's not isotropic. Okay, so the closed thin wall tube. Okay, so when the thickness of the thin wall is much smaller than tube radius, okay, the product of shear stress times the wall thickness is constant. And shear stress is inversely proportional to wall thickness. And the total torque T is, we can just take the integration, right? So we look at this small element. So this T is much smaller than the R, right? Okay. So when we apply a torque, there's a shear, maximum shear, right? Stress on the surface of the tube or solid rod, right? Okay, so we can figure out this area of this triangle right here. We can regard this as a triangle. And the radius of the triangle, dA equals to half times RDS. The ds is the arc distance, right? The arc distance. And the n represent the median line. Okay, so this triangle is the area with the bottom length of the median line. Okay, equals to half of R times ds, right? Okay, so we can take the integration. We can get the torque T equals to take the integration, the shear stress, right? The shear stress right here times uh T times R times ds. Okay, so T times R times ds, what's the area is of this term? R times ds right here, right? It's the twice of the area, right? The twice of this area in regards to the rectangular, right? Like this. R times ds, R times ds, right? R times ds. Okay, so R times ds represent the 2 am. Okay, so we can figure out the total torque applied to a thin wall equals to 2 times am times t times tau. Okay, so am is the area enclosed by the section median line. Okay, section median line. Okay, so from the last course, we already know the shear stress applied to the thin tube and the rod, right? So we can rearrange to figure out what is the shear stress is, right? The tau divided by 2 amt and the twist angle. Okay, so previous slide, maybe for the previous courses, I used the phi, okay, the same thing. Okay, I use the same thing, okay. Equals to the torque times the length, okay, divided by 4g. G is the rigidity, right? Shear rigidity times the am squared times t. Okay, and the lm is the length of the sorry, lm is the length of the section median line. Okay, it's this line. Okay, this line. So for the solid rod, we already know the twist angle equals to TL over JG, right? Right? For the solid rod. Okay. So for the thin wall tube, the twist angle equals to TLN divided by 4G AM square T. Okay, square T. Okay. Okay, stress concentration. So when the component was suppose say a plate with a hole with diameter is D, and we apply the stress, right? The distributed stress, right? So there must be a stress concentration along this hole, right? There's the highest stresses along this hole. So we can define a vector called stress concentration vector, AT, or the stress shear stress concentration vector. Okay, one is shear, the other is the normal stress. Okay, and the stress concentration effect is commonly ignored for static loading on ductile material. So suppose we have the ductile plate apply on stress, constantly static loading. So in this case, well, we don't have to take this stress concentration effect into account. Okay, so and if this case is not static, it's dynamic loading, or it is the brittle materials, we have to consider the stress concentration effect. Okay. Okay, so we can check the table with our textbook. Okay, just a table always. Okay, so this table collect tons of the experimental data. Okay, suppose we have this kind of this plate and with a hole, right? Having a diameter d, and we apply a force. So based on the geometric relation, which is corresponding to its stress concentration vector. And also, if we want to design a shaft, right? A shaft. So with its geometric vector r over d, r is the fillets, the radius of this fillet, the radius, and the d is the lowercase d represent the small shaft, and the capital D represent the diameter of the larger shaft, right? So we get a two geometric relation. One is the r over d, lowercase d, and the capital D over the lowercase d. So what we get, suppose this capital and lowercase d are fixed. So if we have the higher radius of the fillets, we get the what? We get a smaller stress concentration vector, right? We get a smaller concentration vector. Okay. Okay, so it can be used in the bearing design. Okay, bearing design. So the first one, you have the sharp radius and the large radius undercut right here, right? And the figure B shows the shoulder relief groove if we just design with the groove here. So you can figure out its stress distributed line become more smooth. Okay, become more smooth. Okay, and also if we design a large radius of relief groove, we can design a groove here. Okay, we design a groove here. So basically, to reduce the stress concentration, you have to follow some rules. The rule of thumb are increasing the radius and reducing the disruption. Okay. Also allows the dead zone to shape the floor lines more gradually. Okay, so this floor line, okay, the stress will now like this. Okay, will be like this. Okay. Okay, so curve beam in bending. So suppose we have the thick curve beam, but not a beam. So what's the differences from the beam? The difference is that the neutral axis and the centroid axis are not coinciding. And the bending stresses does not vary linearly with distance from the neutral axis. What's that mean? That means, suppose we have the neutral axis, Rn, right? And the centroid axis right here. And these two are not coincide with each other. There's a distance E. Okay? And during bending, we can analyze the specific element, small element right here. And we define as distance from the center of the radius curvature is R. Okay? Okay. right? This is what I mentioned previously. So we have to know the H symbols. So R naught represent the radius of the outer, okay, outer curve beam, and the Ri represent the inner radius. Rn represents the radius of the neutral axis. Rc is the radius of the centroid axis. Okay, and the H is the depth of the section. How depth of the section. And the C naught is the distance from the neutral axis to outer surface. And Ci is the distance from the neutral axis to inner surface. Okay, and E is the distance from the centroid to the neutral axis. And M is the bending moment. Okay, it's the bending moment. Okay, and also this symbol Y, right? Right here is the distance between R and Rn. Okay, R and Rn. Okay, so first we can figure out what is its neutral axis is, right? Where is it? And the stress distribution. So this is for the curve beam, right? It's for the curve beam. So what is the stress? Normal stresses for the regular beam. It's sigma equals to mc over I, right? So where's the Rn minus R? Rn right here minus R, right? Rn minus R is Y, right? Sorry, Rn minus Y, sorry. Rn minus Y equals to R. Okay, so the distance of these sections to the center of the radius of curvature. Okay. Okay. So when Y equals to Ci, what's that mean? When R equals to Ci, sorry, when Y equals to Ci, that means when Y here equals Ci, Ci is the, right, to the inner face, right? From NA to the inner face. That means here, right? This distance. Sorry. This distance, right? Means Y equals to Ci, right? Right here. So with Y equals to Ci, Y equals to Ci. So the Rn minus Ci equals to Ri, right? The same, this is similar with Y equals to C naught, right? When Y equals to C naught, and Rn minus C naught equals to R naught, right? So it's Y equal to Ci, and Y equals to C naught. So we can figure out when the curve beam undergoes the pure bending, what's the stress along this inner surface and what is stress along the outer surface. Okay, right? For the inner surface and for the outer surface. Right, so there's some example for the hook. Okay, so maybe if you are a gym guy, so you're gonna work out every day, so you know how those buckle or some hook, well, can be used in some machine work, right? Some machine work. Okay, so I'm gonna skip this example. You can just figure out by yourself. Okay, and also for this formulas for section of curve beam, you can check your textbook or some handbook, okay, for the different cross section of the curve beam, and we can use this table to figure out what is RC, where's the RN is, okay, for the different cross section, okay, for different cross section. Okay, so today's course will be ended here. So if you have any questions, just feel free to email me.